400 billion stars in the Milky Way alone. Conservative estimates put the number of Earth-like planets in the habitable zone at somewhere between 300 million and 40 billion. The math says the galaxy should be full. The physics says we should have made contact by now. And yet, silence. Total, unbroken silence. Physicists call it the Fermi Paradox. Enrico Fermi posed the question in 1950. Over lunch. Not in a lecture hall, not in a published paper, over lunch at Los Alamos. In 1950, Enrico Fermi was sitting at a table with some of the most brilliant physicists on the planet. The conversation drifted to UFOs, a topic the press had been running with for years. Fermi looked up and asked a question so simple, it stopped the table cold. Where is everybody? That question became the Fermi Paradox, and in the 75 years since, nobody has answered it. Here is the core tension. The universe is approximately 13.8 billion years old. Earth is 4.5 billion years old. That means other civilizations had a 9 billion year head start on us. Even at a fraction of the speed of light, a civilization that emerged just 1 billion years before us could have colonized the entire galaxy by now. Every star, every planet, every signal band. And we hear nothing. No signals, no megastructures, no coordinated light patterns, no transmissions in any frequency we have ever monitored. The SETI program has been running since 1960, 64 years of listening. Silence. The Drake equation, developed by astronomer Frank Drake in 1961, tries to calculate how many communicating civilizations should currently exist. Depending on the variables you use, the answer ranges from tens of thousands to millions of civilizations, active in the Milky Way right now. The signal we should be drowning in does not exist. That is the paradox. In 1998, economist Robin Hanson formalized what he called the Great Filter. The argument is straightforward. If the Drake equation says intelligent life should be common, and we observe no evidence of intelligent life beyond Earth, then something must be filtering it out. Something between the formation of a planet and the colonization of the galaxy is catastrophically difficult. So difficult that virtually no civilization clears it. The filter. The question that keeps physicists and philosophers awake is this: is the filter behind us or ahead of us? If it is behind us, if the filter is something like the development of complex cells, or sexual reproduction, or the emergence of consciousness, then we may have already cleared it. We may be the rare exception, the one civilization in a billion that made it this far. That would explain the silence. If the filter is ahead of us, if it is nuclear war, or climate collapse, or artificial intelligence, or something we have not yet imagined, then the silence means something else entirely. It means every civilization that reached our level eventually hit something they could not survive. Let us run the physics. 9 countries currently possess nuclear weapons. At peak, the United States and the Soviet Union held a combined arsenal of over 65,000 warheads. The yield required to trigger a nuclear winter, a global temperature collapse that would end agricultural civilization, is estimated at as few as 100 detonations. 100 out of 65,000. Nuclear risk researchers at the Future of Humanity Institute estimated the annual probability of a large-scale nuclear exchange at approximately 1% per year, under stable geopolitical conditions. That number rises sharply during periods of miscommunication, technical failure, or direct confrontation. There have been 32 documented incidents since 1945 in which a nuclear exchange nearly occurred. Not almost war, not political tension. Incidents where missiles were on the way and were stood down at the last possible moment. 32 times. Now apply that to the Drake equation. If every civilization that reaches nuclear capability faces a 1% annual extinction risk, the math is not gradual. It is geometric. Over 1,000 years, a window that is essentially zero on a cosmic timescale, the probability of survival drops below 0.0004%. The number changes dramatically. What happens when you insert that survival rate directly into the Drake equation is the part nobody in this conversation has been willing to say out loud. Stay with this. Frank Drake's equation has 7 variables. The last one, the average length of time a civilization remains detectable, is the variable nobody agrees on. Drake himself estimated it in the thousands of years. Optimists push it to millions. We did not estimate it. We calculated it from the physics. If the annual extinction risk from nuclear capability is 1% under stable conditions, and the historical record suggests instability is the norm rather than the exception, then the average civilizational lifespan after nuclear capability is not thousands of years. The model produces a window of between 200 and 400 years. Insert that into the Drake equation. The expected number of currently active, detectable civilizations in the Milky Way collapses. Not gradually, immediately. The range that previously produced tens of thousands of civilizations now produces a number between 0 and 1. 0 and 1. That is not a rounding error. That is the physics telling us something. Every civilization that reaches nuclear capability enters the same probability window, the same geometric decay, the same filter. And the filter does not care about intelligence or culture or the intention to survive. It only responds to the math. And the math is not on our side. Now, here is the objection this framework invites, and it is a serious one. 1% annual risk is an estimate, not a measurement. The Future of Humanity Institute's figures are modeled projections, not empirical constants. Different researchers produce different numbers, some as low as 0.1% annually. And if civilizations develop better governance, better communication, better early warning systems, the risk could decline over time. We could be the civilization that breaks the curve. We ran that objection. At 0.1% annual risk, the most optimistic credible estimate, the survival probability over 10,000 years is still below 0.01%. The curve still collapses. It collapses more slowly. The conclusion does not change. On the question of improving governance, the historical record does not support a consistent downward trend in nuclear risk. The Cuban Missile Crisis occurred 13 years after the first test. The Stanislav Petrov incident, in which a single Soviet officer chose not to report a false missile alert that would have triggered retaliation, occurred 38 years after the first test. The risk did not decrease with experience. It became more complex. The 32 near-miss incidents are not distributed in the early years and then tapering off. They are distributed across the entire timeline. Enrico Fermi asked, "Where is everybody?" over lunch at the facility that built the first nuclear weapon. The answer may have been in the room with him. The Great Filter is not a mystery event in the distant past. It is not a cosmic ray or a gamma burst or a rogue asteroid. It is the physics of the weapons we built ourselves, applied to the probability of our own survival, extended across a timescale we have never seriously calculated. When you run that calculation, the silence makes sense. Not because the galaxy is empty, but because the window between nuclear capability and either extinction or transcendence is extraordinarily narrow. 200 years, 400 years, a blink. On a cosmic clock running for 13.8 billion years, a civilization that exists for 300 years and then goes silent is invisible. The signal never reaches anyone. The silence is not evidence of absence. It is evidence of the window. And we are inside it right now. Want some more interesting videos like this? Check out our old videos.